Good morning, everyone. My name is Tom Hillman. I'm a principal consultant with XML Limited, where I spend most of my time working with XSLT for the publishing industry or giving XML technology training courses. Today I'd like to spend some time talking about a personal project, an open source Invisible XML implementation based on ideas from the Earley parser and written in XSLT. I call it the JayParser, which is a nod to J. Earley, who wrote the Earley parsing algorithm. In February at XML Prague, I gave a talk on the proof of concept, but I ran out of time before I got to talk about any of the code details. I hope to rectify that today and share some of the progress that has or hasn't been made since then. However, before I tell you about the code, let's cover some parser basics and establish some vocabulary and see if I can explain a little bit about the Earley parsing algorithm. In this case, when we talk about a parser, we're talking about a program or algorithm that takes two inputs: a string, which we want to parse, and a grammar, which tells us the parsing rules. Parser takes these two things and attempts to understand the string according to the grammar. In our case, it does that by returning the information in the string as a marked up tree structure, such as this one. The grammar is the key to recognizing the information in the string conforming to the syntax of a language that the grammar defines. Invisible XML belongs to the EBNF family of grammars and defines syntax using symbols. Symbols can either be terminals, that is, they represent literal text or match patterns in the input, or non-terminals, rules which themselves are made up of symbols. Grammars may also define repetition and optionality of these symbols in much the same way as we're probably all familiar with from regular expression tokens, DTDs, or schema. Note in this example how each line represents a grammar rule. Each rule starts with a non-terminal name followed by a colon, and then followed by a sequence or combination of terminal and non-terminal symbols. Mentioned Invisible XML several times already, we probably ought to define what it is. Invisible XML was invented by Declarative Amsterdam's own Stephen Pemberton in 2013, and it states that since all data is an abstraction, any representation of the same data can be thought of as equivalent, whether it's in XML, JSON, or some other markup language. In other words, regardless of how it's serialized. If it can be parsed with a grammar, then, we can treat it like XML and use all of the XML technology stack when we deal with it. The core of Invisible XML, then, is a grammar language that includes features that control how a parser serializes an input into an XML tree by converting selected non-terminal grammar rules into elements and attributes, and terminal values into text nodes and attribute values. Next, it's helpful to consider the Earley algorithm. Here are some useful terms. The state, or state number, is a reference which stores the input, which we have yet to parse. Rules map one non-terminal symbol to a sequence, or a combination of sequences, of terminal and non-terminal symbols, just like we saw earlier in that grammar example. Traditionally, the Earley parser starts by evaluating the first rule of the grammar and then uses it and the symbols it references to build a table of Earley items. These Earley items store things such as the current rule being tested against the input, the position in the current rule as the rule is processed, the current state that we're processing the rule in, and the state when the rule evaluation began. So these can be thought of as a series of atomic parses, sort of partial parses. And we can also talk about items which complete a rule, that is, where we've reached the end of a rule definition. Eventually, the table should contain an item that completes a rule that starts at the initial state and ends at the end state. That is, a parse that contains the entire string we wanted to parse. And this gives us a valid parse. Actually, there may be more than one valid parse result, and it should be possible to generate every one of them from the complete table of Earley items. This means that the Earley algorithm can cope with ambiguous grammars. So this should give us enough vocabulary that we can actually start to talk about the implementation. Let's do that. Earley tables and Earley items sound well and good, but one of my goals for the JayParser was to write a parser that could be extended by XSLT developers, for instance to dynamically expand entity substitution. Since what we want out of the process is a tree, I wanted to find a way to make the most of XSLT's template matching and tree handling. So I began to explore the idea of making a tree instead of a table, an idea inspired by Michael Spurberg-McQueen's paper on the subject at Balasage 2017. In an Earley tree, rules are stored as elements, which contain one or more alternative parses, themselves containing further trees as representations of the symbols of that rule. The position within the rule in an Earley tree is simply the document position within the tree. State I chose to store as an integer, which refers to the index of a sequence of all possible states. There are other more efficient ways of doing this, but remember I hoped one day to do things like entity substitution, so I need to choose a way which will let me change the input string as it is parsed. To eliminate duplication of effort and risk of infinite recursion, we also need to store a map of visited rules and states. Terminals are held as leaf nodes, and visited non-terminals are recorded as references so that they can be reconstructed later. It turns out that the Earley tree that gets created is what's known in parsing circles as a type of parse forest, a set of possible parses, valid or invalid, combined using AND or relationships. Thanks to Michael Spurberg-McQueen for pointing that out to me. So all we need to do to return a valid parse is to prune away all of the invalid parses and empty parses and choose any one from the valid parses. We exclude empty elements or any non-terminals that fail to complete. We copy and then expand non-terminal references that do complete. And where there are alternatives, we simply choose one. In our case, we simply take the first, and then remove the now unnecessary other choices and structural elements that represent the choice. Here's the proof of concept example from XML Prague this year, a very simple input file and the resulting XML representation. Here it is as a tree. The two inputs to our parser are normally presented as strings. The string which is to be parsed, which we want our parser to represent as a tree, and the grammar itself. But the Invisible XML specification defines its own grammar. This means that the Invisible XML grammar itself can be represented as an XML tree. It seems to me that XSLT's strongest use case is when transforming trees, especially tree-to-tree transformations. So it makes sense that the JayParser uses this XML representation as the tree input in a tree-to-tree transformation, processing it with the input string as a parameter, and then pruning the resulting Earley tree. Let's take a look at a couple of the structures that we need to use to do so. As the Earley tree is created, we need to know whether each rule or set of alternatives being processed have already been processed in the current state. If a rule has already been visited, we will also need to know which states might result, so that we know where to continue processing. This is stored as the visited map, which can be passed as a tunnel parameter through the process, and is a manifest of which rules have been visited in which state. This map not only needs to check each time a rule is visited, but needs to be added if the rule has not been encountered, or updated if a rule results in a complete partial parse. We also have the idea of the states sequence. A state in JayParser is a number, an integer, which itself represents a stored string, which I shall call the state string. Specifically, it is the index of that stored string in a sequence of all possible state strings. These state strings represent the part of the input string which is yet to be parsed. This sequence of state strings also needs to be updated as the Earley tree is created, with the new state string being added every time a terminal symbol correctly matches the current state string. This need to update the visited map and state sequence before processing the next node at any given point is probably the biggest challenge in writing the JayParser. We can't simply process all of the children of any given node, because each node depends on the values of both of these variables that result from processing the previous node in document order. That means the visited and state information needs to be passed from sibling to following sibling, and from the children to the parent, and not, as is usual, from parents to children. Tunnel parameters then will only get you so far. They pass information down the descendant tree. We need to override the default processing order then, preferably doing so in a way that preserves the whole pool processing idea of XSLT. When working on the XML Prague proof of concept, I decided to use a couple of named templates wherever I would normally have applied templates to children of a node. These process children's nodes as a variable before returning a parent node, sort of processing the tree from the leaves back to the trunk. I then calculated visited and state information separately for each node, using custom functions and modes. I wasn't very happy with this at the time. It seemed inefficient as you were essentially processing the same node multiple times, and it turns out that there were more fundamental flaws in using this approach. It is hard to ensure that building these data structures in this way actually produces consistent values for siblings in the grammar input. So the proof of concept for XML Prague was designed to work for one given grammar, but not yet a general case. Additionally, it did not make enough use of some of the XSLT3 features that are now available to us, so I decided to rewrite the parser. In the mode that builds the Earley tree, for all but the most outermost template, I decided to return not just the Earley tree, but a map for each template that was being used. This map includes the Earley tree for each child, but also the states definition and the visited map. Templates can combine maps intelligently, retaining updated visited and state information, and combining the Earley tree leaves and saplings, ensuring that each node only needs to be visited once and information remains consistent. We still need to use a named template approach, but rewriting these to use XSL iterate resulted in a much more readable, understandable code than the previous mechanism, which used recursive apply template instructions. The Invisible XML specification itself suggests an approach for implementing options and repetition, Since the grammar language already has structures to deal with alternatives and empty results from parsers, we can rewrite optional symbols and symbols that repeat. Here's an example that rewrites an optional repeat, repeat 0. Note that this template, together with nearly all templates of this mode, returns the map containing not only the Earley tree, but visited and state metadata. First of all, we create a unique ID for the repetition using the local name and the generate ID function, local name being there primarily for debugging purposes. We can use this to add to the alternative structure to the visited map, which should ensure that we don't get stuck in infinite loops. Next, we build an alternative structure using the same model as the input grammar. This is stored here in the variable equivalent. An optional repeat is really equivalent to the two alternatives of an empty parse or else a non-optional repeat, repeat 1. Since this returns a single element, we can simply apply templates in the parse tree mode, which we know will also return a map. Since we're using the repeat 1 definition here, we probably also ought to have a look at the non-optional repeat. It looks fairly similar. Again, we're looking to return a map, and again, we're generating an ID for use with the visited map. Actually, we saw in the optional repeat example previously that we specified this ID as an attribute in the rewritten equivalent variable. We need to preserve this value as we rewrite parts of the tree, since every time we create one of these equivalent variables, they are technically a new document and will have a different generate ID value. A non-optional repetition is equivalent to the content of whatever's being repeated, followed by an optional set of any defined separator, together with a copy of the original repeat. Note how we preserve the use of the GID to make sure that we do not get stuck in an infinite recursion loop. We can also deal with optional symbols in a similar way. So much for the theory. How does it work? Let's actually take a look at a demonstration here in Oxygen. So this is the current state of the JayParser, and as an input string we're going to use our example string from the proof of concept in February. Here's the corresponding grammar. You can see that there's a bunch of rules that describe a program. Our program has got a block and then a statement and an assignment. Some of these rules are marked with a hyphen to show that they shouldn't create corresponding XML entries and will be replaced with their content. Let's have a look at what it produces. Here we are. This is what was wanted. Program, block, statement and an assignment. You can see that the terminal symbols have been turned into text strings, and the rule definitions, the non-terminals, are used as element names. That doesn't really illustrate very much either, so let's just very quickly tweak the result of running this template to show us the parse tree instead of the finished parse. You can see there's a lot more information here, and those 6 characters actually produce a parse tree hundreds of lines long. You can see that when we've encountered a rule, we've created a rule element. It says which state the parse starts in and also which state it ends in. In this case, every character in the sequence is a terminal symbol, so there are 6 possible states that we deal with. And you can see the block itself also contains the entire string. The first literal we encounter is the open curly brace, and we can see here how a literal is captured. The beginning state and an end state, and the curly brace as a text node. If we have an optional element, such as white space, we can see that one of those options is the empty. And we can also see what happens if a terminal symbol fails to match. We get a failure. This doesn't mean that the entire parser's failed, it just means that this subtree has. Here you can see that a partial parse may produce more than one valid end states, representing repetition. And here we can see a visited non-terminal reference. In this case, we've already looked at what rule may be fulfilled by looking at the identifier rule in second state. Examining then some of the templates that are being used. The first template in the parse tree mode here matches the overall grammar. This is the only one that doesn't produce a map. But we look at the map that would be produced by applying templates to the first rule. Some debug features, and then what's returned is the parse tree from that map. Every other template in this parse tree mode returns a map. Looking at rules or alternatives are handled in much the same way. First of all, we have to check to see whether the rule or alternative has already been visited. If it hasn't been visited, then using the result variable, we can process its children using the name template process alt siblings. This is because both rules and alternatives both use the alt child element and can be handled in the same way. We make sure that we parse our visited tunnel parameter. Then we take that result and build a new parse tree, update the visited map, and copy any other metadata from the resulting map from processing the children. If the rule has been visited and it fails, then we know that this rule has also failed. If the rule is visited and succeeded, then we can replace it with a non-terminal reference. Children of an alt element, on the other hand, are not alternatives and need to be called using a different named template to process siblings. We'll look at both of these named templates in a moment. Again, the parse tree is returned as a map along with the metadata that results from processing the children. Let's have a look at the name template process siblings. This uses an XSL iterate statement to preserve the results of the visited and states metadata from one sibling to the next. If the previous sibling results in a failed parse, then we can break out of the iteration since it's of no further use to us and will never result in a valid parse. If it succeeds, however, we need to be aware that the previous sibling may have had a number of potential end states, and we actually need to be able to process each of these in turn. This is the third call template alt states does. It's really just there for brevity. What alt states does is it looks at the map for the previous node and counts whether or not there are more than one potential end states. If there are less than or one potential end states, then we're very happy, and all we have to do is apply templates on the node with the updated state and visited metadata. If there is more than one potential end state for the previous node, then we actually need to evaluate the results of running the current sibling starting at each of the potential end states. Again, we use XSL iterate. Finally, let's have a look at processing alt siblings, that is, processing siblings of alternate options. Again, we're using XSL iterate. The difference here is how we combine the metadata for states. The visited metadata is still preserved and passed along the iteration, but the ends need to be collected across all of the alternatives for the parent metadata. So that's quite an in-depth look into the workings of the JayParser. Next question is, how well does it actually work? Well, before we get to that, I'd like to spend a little time discussing what it means to be an implementation of Invisible XML. In a sense, it's impossible to say that the JayParser is an Invisible XML implementation, because the Invisible XML specification is still in beta, and there is no conformance suite defined as yet. The good news is that a working group has been formed since Balassage this year, and Stephen Pemberton, Michael Spurberg-McQueen, and myself have been meeting monthly, and that we are looking at defining and publishing a conformance test suite, as well as bringing the specification out of beta. Of course, we would welcome involvement from the wider community. My primary method of testing is a modified version of the dog food test, parsing the invisible grammar itself. I've slightly tweaked it to ensure that there's an example of every rule represented, and I hope that if I can get a successful parse, this shows that I have a full implementation. In terms of progress, I'm afraid it's not as good news as I'd like to give you. After the rewrite, my proof of concept grammar still works, and my goal of implementing Invisible XML itself has made some progress. The new code attempts to implement all the features, but some grammars, such as the dog food test, are still getting stuck in infinite loops, a sign that there are still some bugs around the rewriting of repetitions. However, that's not the biggest issue. Although my sense is that a working parser is actually very close, I've just run out of time, I think a bigger issue seems to be with the performance and scaling. Parsing the Invisible XML grammar itself currently takes nearly an hour before failing and gets about a third of the way through the grammar. There is still plenty of work to do, which leads nicely to contributing. JayParser is available on GitHub, and if anybody would like to have a look at the code itself, or, dare I say, wishes to contribute to the project, those contributions and interest would be very welcome. Thanks for listening to my talk. My apologies for anyone hoping to hear of a complete and working parser implementation that they can use in their XSLT. All I can say is that sometimes success is merely iterative failure, and I haven't given up quite yet. Thank you.